Hi everyone. Today's topic is about the nodal analysis, and this is the most important topic for production engineers because this is a routine job that they do always, and most of their decisions of production engineers they are depending upon this nodal analysis. And this nodal analysis is needed to design the tubing string, to design the pipelines, to not only to design it but to operate it efficiently. So this is the most important part for nodal analysis, and I hope that from this chapter you will get some benefit out of it. So let's start with first of all, let's first look at the production system. As a production engineer, what is our responsibility? First of all, we have as you know that we have a reservoir. Definitely reservoir is not that simple as we see, but we usually say like this, that we have oil, water and gas. So we have three zones, 1, 2 and 3, and based on the density we say that the above part is the gas, this we say is the oil, and this we say water. Usually the reservoir is composed like this. Then what we do, we put the well. Okay, we put the well like this. Okay, inside this well we put the tubing string here, and we close it. So, and then from here we have pipes and separators. This is the separator. Okay, so now as you can see that we have the porous medium. This is the porous medium, we call it. We have the completion, the second part. This is the completion tubing that we talk about. Okay, this vertical part, inside there are lots of safety valve inside, and then we have this line and the separator. So we have four parts basically here. Now as a production engineer, this reservoir is not managed by the reservoir. It's the job of reservoir engineers to manage it. But as soon as the oil comes inside this plumbing system, inside this pipe, this is our job then. So we have to manage this part. Okay, this part and this part and this part. These three parts we have to manage it. And what we have to do, we have to manage the pressures. Okay, we have to manage the pressure, average pressure within the drainage boundary. Okay, okay, if the pressure changes, the well's performance changes. The well needs to be reevaluated. So by time, okay, when we have this reservoir, okay, we have the reservoir after, for example, if the initial pressure in in 2018 pressure was 2000 psi, but in 2020 the pressure dropped to 1700 psi. So now when the pressure drops of the reservoir from 2000 psi to 1700 psi, everything has to be reevaluated. All this completion string, the pipeline performance, the separator performance, the tubing walls, everything. We have to reevaluate everything. And how we reevaluate it, we do the nodal analysis. Usually we talk about the IPR and vertical lift performance. So we have to reevaluate everything. Or if, for example, you are monitoring the production history. Okay, production history. Production history says in 2018 water production was 20 barrel per day. Okay, in 2019 water was 200 barrel per day. In 2020 water was 1000 barrels per day. So now within 2 years the water production increased from 20 barrels to 1000 barrels. So now everything has to be reevaluated. Normally we do every month actually. We don't wait for 2018, 19, 20. Most production engineers, they evaluate their production well performance uh, every month. Now, based on this nodal analysis, not only the production performance can be of two types. For example, individual uh, individual well performance. This is one thing, or field performance. We have to look at both. So for the individual performance, we go for Prosper. We do the IPR. We look at the water production. We look at the pressure drops. We whatever parameters we have, we evaluate their performance, and then we look at the field performance. We have to prepare the chart For example, how much field is going to produce in June 2020. So we can tell the company, okay, we are capable to produce 50,000 barrels in June. Okay, 60,000 barrels in June. So you give an estimation to the company owner so that they do the contracts with the buyers. Okay, in June we can produce 50,000 barrels. In July we can produce 60,000 barrels. Or if there are some changes, for example, the water production is increasing or something, so they definitely tell the management that this is the production problems we are facing at this time. So we have to evaluate the individual performance as well as the field performance. So now let's, it's a very nice diagram, and probably you'll see this in exam also. So now you see that we have a number of parameters here. We have PE, okay, we have PWF, we have PWF here, we have production here, we have here, 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 here. So we have lots of P8s, 1, 2, 3, 4, 5, 6, 7, 8. Now this part is related with the reservoir engineer. If the pressure drops here, if there are some problem with the reservoir engineers usually handle it. But as the production engineer, we are definitely careful for these perforations, how they are performing, how big they are, how small they are choked, they are open, they are plugged, they are unplugged. I mean, what is their size, how much is their length, should we redo the perforations, or I mean, we have to evaluate this. So we have to look at the pressure losses across these perforations. So the second one, the loss in porous media. If there are losses here near the wellbore, we look for the stimulation job. So if there are losses, what can we do in this case? For example, if there are losses here in this one, we go for stimulation. Okay, stimulation like hydraulic fracturing or acidizing. If we face problem in this one, we look for you can say that reperforation, perforation, or you can say workover job. These are all workover jobs. Okay, if there are restrictions here, for example, in the third parameter, or you can do the third one. So we go for actually re uh, change the walls. It's a costly job, but we have to do it. Okay. So anyway, let me complete it. So there are pressure losses from this point. There are pressure losses from this point to this point. The pressure from here to here, pressure drops. Then from here to here, the pressure drops also. Then from here, when it goes inside, the pressure drops also. When it goes through the restriction, pressure drops also. This one, here it drops. Then it drops here. Then it drops here. Then it drops here. So for example, the pressure here was, let's say, 2000 psi. 2000 psi. Here it maximum you can have 100 to 400 psi. So the pressure drop from 2000 psi, all this pressure is all inside this plumbing system. Okay, and our job is to optimize it and to reduce these pressure losses so that we can produce the maximum. So nodal analysis actually says we select any point. Okay, we call it a node. For example, you can select any point. For example, you select uh, this perforation. So you selected this perforation and you can call it as a node. You, okay, you say it as this is our node, and you look at it and how you can reduce the pressure losses. Okay, your job, reduce pressure loss here. Reduce pressure loss. So you reduce the pressure losses here. Okay, and that's our job as a production engineer. We reduces the pressure losses. We reduce the pressure loss here. But the question is how we can reduce the pressure loss. First, we need to understand whether the pressure is lost here or not. This is the first question. So we look into it, and then we go ahead further. What can we do with it? So we have 8 different pressure losses from reservoir to the sand face pressure, from sand face inside the perforation, then it goes when it goes to the tubing string, inside this gas lift valve, then if you have triple HP safety valve, then you have here at the Christmas tree, then inside this pipeline diameter, then finally when it goes to the separator. So there are lots of pressure drops that we can do. So what, as I said, what we do, we select any point in the production system where we think that the pressure is lost. So we look at it, how much the pressure is lost. So after we look at it, then we optimize that node area. So now we have two extreme, as I said. We have this one. Okay, okay, one is here and one is here. So we have two different one, and let's look at. We can optimize it. These are the two extremes uh, points that we have. So the at extremes, the number 8 we call it the average reservoir pressure and the separator pressure. So here we call it the average reservoir pressure at this point, and here we call it as a separator pressure. Between them, the lots of pressure is lost, and as a production engineer, our job is to control it. So these are the nodes we have: 8, 7, 6, 5. So you select any point in the system, any point, and you optimize. You look at the pressure losses, and then you try to fix it to improve the pressure, so that you pressure do not lose inside the system. That's our job. Okay, so now, as I said, our objective is to look at the pressure losses at each of the point as we are talking about. Now, this pressure or pressure loss is directly uh, connected with this flow rate. So, pressure loss and flow rate, they are both connected. Higher the flow rate, more will be the pressure loss. So, these two are connected with each other. Okay, so flow rate is functionally related with the pressure differential across the component using this equation. So what we do in nodal analysis system, we combine both all the components and we optimize the pressure losses based on the flow rate. That's our main job. So, and what is the idea behind it? We connect the flow rate with the pressure drop, functional pressure drop. That's what we do. And how we connect them? We have an equation. We have a relationship. We call it the inflow performance relationship. So it's a functional relationship between the production rate and bottom hole flowing pressure. So you can see that it's a relationship between the flow rate here and the bottom hole flowing pressure. Okay, so for example, when the pressure of the well is shut, when the pressure well is shut, it means that there is no flow. When there is no flow, we are dealing with the reservoir pressure, means the original reservoir pressure. But as you start flowing, if you go ahead, as you start flowing, okay, as you start flowing, the pressure starts to drop. You can see it's better. So when you produce the maximum, means maximum, like, which is, this is theoretical, like this is not possible this point. But if you unlimitedly produce it, the pressure will become zero. That's the point. So anyway, the point is that the more you produce, and the pressure will be dropped. Now, for example, at this point, at this point, okay, the the flow rate at this point, let's say the 1000 barrels per day. So at this point, what is the pressure? So you can take the pressure from here. Or for example, you are producing 2000 barrels per day. So what will be the pressure drop? Or what will be the flowing pressure? In this case, we are dealing with the flowing pressure. Okay, these both terms are important. Now, this one tells us from 0 to maximum flow rate. In the well, you can take 3 points. For example, you let the well produce at 1000 barrels per day, or you produce it at 1100 barrels per day. You take 3 points and then you make this line. Okay, this IPR. And once you take 3 points, you find its slope, and then you can construct this line. This tells us that if you produce at this much pressure will be lost. And if that's what, because our job is to control the pressure losses. So this tells us how much will be the flowing pressure if we are producing at this well. Or if the pressure is not behaving like this, then what is the problem? So we monitor the IPR in much detail here. And it's very important parameter as a production engineer. Okay. So, and remember, this straight line shows that we have the reservoir under saturated condition, when the reservoir is above the bubble point and uh, there are no two phases and gas is totally dissolved, and we produce single phase, which is the liquid in this case. Okay, productivity index concept is not used for gas well, as the IPR for gas well is not straight line. So this IPR concept and this thing is only valid for oil wells. it is not valid for the gas wells. This is the point. And now let's look at some example. We have equation to calculate the flow rates. Okay, we have thickness, we have initial pressure or flowing pressure, formation volume factor, viscosity, wellbore radius. We put it. Now let's look at the impact of the area, or the skin permeability and this skin. First of all, we put everything same. We just change the value of the area here. Okay, area can be changed when you change this, the external radius feet. So when you increase the external radius feet, okay, the ratio is definitely increasing also, and you rate that rate is decreased. So for example, if we have the well, if we have the well, and if it is producing from this zone, is fine. But if it is producing from a larger area, the well pressure will decline, and if producing more larger area, the flow rate will further decline. So it tells that if you increase the drainage area, means that the area this well is draining the oil. I mean, okay, area this well is draining the oil. And draw it again. For example, this one. This is the well. Sorry, my drawing is bad here. I'm just why it is lost. This one, this one, and the drainage area is the area from this point till this point. So this is the drainage area. The more the distance of the boundary towards the well bore, the less will be the production rate. So each well, that's why we put number of wells. So if the drainage area become less, so that we can produce more. That's the point. So it should produce from the nearby uh, vicinity. That's it. Or if you want to produce more, you put more well. You put one well here. You put one well here. You put three wells. Then you can produce. But if you have the larger external radius and you put just one well, it will have effect on the flow rates. That's the main point behind it. Then, if the permeability is 10, this is the example of this case. If the permeability is 10, you can produce 1190 barrels. If you put it 1, so permeability is directly related with the flow rate. Okay. On the other side, if you have a skin factor, which is the formation damage, the plugged permeability near the wellbore, you see that if you have the 10 permeability, the flow rate reduced to 519 barrels. So 1190 to 590. 119 to, so you can see 50% almost the production rate has declined because of the stimulation. Now, if we have such situation, when we have this kind of situation and skin becomes 10, we go for stimulation. We do the fracking in. So as a production engineer, we look at it whether we need stimulation or not. So this skin factor, as you know, is obtained from the well test analysis, which is the pressure build-up test analysis and so on. Okay, now we have another one and example, and in this case we just prepare the IPR curve and look at this one. First of all, as I said, drainage area we have to calculate from the area, drainage radius. Okay, and drainage radius has directly connected with the flow rate. And this is the wellbore flow rate, and we have this equation. Simply we just plug in all the information here, and we get the flow rate here. In this case here. And as I said, this is just directly related with the oil above the bubble point. So we calculate the productivity index here, and then we prepare the IPR. Okay, this IPR curve, as I said, is very important when we go for the nodal analysis, and you will see the use of this IPR in the upcoming slides and so on. So as I said, this is the single phase IPR, and now we are talking about the two-phase flow when there is oil plus it has some gas as a second phase. So this two-phase flow usually occur in where? When the we have the gas drive, or we have the solution gas drive, or we have the combination of both. So in this case, the IPR which we dropped previously is not valid. It has to be, line has to be go like this one. It's not going to be straight. Actually, it's going to be curved like this one. So it shows that there are two phases now. So it's a clear indication. Now in this case, we have another method we call Vogel's method. Okay, we have some more methods, but here we are talking about the Vogel. But for example, we have multiple fractures. We have different kinds of carbonate reservoir where permeability is too low, or if it has asphaltene. So IPR is affected from all of them. So we have so many methods. This is just an as an example method we are showing you. But if you go to the software, there or the latest research that we have so many methods that are used to calculate the IPR. Yes. So we have so many methods to calculate this IPR for two-phase flow, and one of the method is Vogel's method. This is the old one, and we don't use it a lot. We have so many other good methods now, modern method which uh, which consider many other parameters and so on. So in order to calculate the IPR, which is the relationship between the flow rate and the flowing pressure, this is the two-phase flow IPR that we have to make using the Vogel's method. The first thing we have to find out is we have to calculate the Qmax. Once we have the Qmax, okay, which is based on the bubble point pressure. Once we have the Qmax, we put it in the equation and we calculate the flow rate at different flowing bottom hole pressures. Here at different bottom, an example you can see. I will show you. So in the bubble, when the well is undersaturated, we use this equation to calculate the flow, the productivity index. But when we are less than the bubble point, means we have two phases, we calculate using this one. Now here, what is M? M is this equation that is based on the Vogel's method. So now it means that the IPR calculation for the single phase and two phase, they are different. So if not only if one phase and two phase are different, it means that if the well has fractures, if the oil has asphaltene or any solid, so it means that this is not going to be valid. So you have to choose the right method to calculate the IPR when you are going to design the production system. And now for this, in this case, you have to go to through the One Petro website and see what you can do and what are the modern methods. And there's so much literature, so much research is going on in this case. Now here in this case, we are talking about the flowing bottom hole flowing pressure was 1765 in this case, and the reservoir pressure is 2085, and the rate is 282. So first we have to calculate the productivity index, which is used to calculate the IPR. We producing rate. Now if the well pressure is reduced, how much will be the production rate? Okay, and or if the production rate we want to uh, produce at 400 stock tank barrels per day, so what will be the flowing pressure in this case? So it's very simple. It's a straight. We are here. Remember, here in this case, we are not talking about the bubble point. It means that we are talking about the single phase. Whenever, what is the bubble point? The first drop where the gas is formed. So in this case, there is no bubble point. It means we are talking about the single phase. So that's why we are using the simple equation, which is for the single phase, and this is the productivity index. Based on the productivity index, we find out the flow rate, 528 barrels per day, and the flowing pressure at 400 will be 1630, simple equation, and maximum oil you can produce is 1835, which is theoretical, is not practically possible. But in this case now, the same pressure, okay, same everything, but we are now talking about the bubble point. So here you can see now 2100. It means the well is now two phase because flowing bottom hole pressure is 1765. It means the tubing string may have two phases. So what we producing rate if PWF is reduced to zero means Qmax. Okay, or if 1400, and or same thing, but now we are talking about two phase. Same first, as I said, we have to calculate the Qmax using this equation as we showed before. So once you have the Qmax, you Qmax is calculated 1997 stocking barrels per day. Then you calculate the flow rate at different PWF. You change the PWF and you find out in this case. So here you can see at different PWF we find out the flow rates. We change the flow rates. Rest all you keep it same in the equation with PR is same, PR is same. Just you change the PWF and you obtain based on this flow rate, this will be the flowing pressure. Now compare it that when we had the single phase and when we have the Vogel. Okay, difference in the result from the two methods is small as long as drawdown is close to the test condition. However, as PWF is reduced to zero, a substantial difference is calculated. So as there is, we are moving towards the zero, uh, maximum absolute open flow potential, there is a big difference is coming up. So when we are producing at 1485, the difference is actually not too much. Okay, but when the pressure drops a lot, then there could be a big issue in this case. Now, in the previous one, we didn't talk about the mechanical skin, okay, or we didn't talk about the positive skin. So in this case, we have to talk about the skin factor and we standings extension. So standing actually extended the Vogel's method and developed the IPR calculation method based on the skin. Because as you know, we are talking about the pressure drop, but when we talk about the skin, the pressure drops more. So here you can see that it's supposed to be like this, but actually it become like this. Pressure drops a lot, and it's due to the near wellbore damage that is happening. So in this case, there's a new term that is introduced, which is the flow efficiency. And when we have the flow efficiency 1, it means the well is undamaged. Okay, if it is more than 1, then it is stimulated. If it is less than 1, then it is damaged well. So we have to calculate the flow efficiency in this case. And once we have the flow efficiency, and also this flow efficiency comes from the pressure build-up test. And then we recalculate the flowing bottom hole pressure based on the flow efficiency. Okay, here you can see flow efficiency. Okay, flow efficiency reduces the flowing bottom hole pressure. Okay, it is obtained through the well test analysis, this flow efficiency, and can be used. So when you talk about uh, the well performance, the pressure drops, you must take care for flow efficiency also in this case. Okay, here you can see the flow efficiency. Based on the flow efficiency, you see 0.5, the producing rate is less. Okay, 1, this is the one. So if it is less than 1, the well is damaged. Here, if stimulated means it is more. So you can see here, this is the one original, but if the well is damaged, the IPR is reducing. This is reducing. If well is stimulated means you do some fracturing job, it's more here in this case. Okay, and this depends on the perforations. Now, in the perforations, we have to look at it that where are the pressure losses. So there are lots of pressure losses that can happen in the perforation, and we have a method, very famous method, the McLeod's method, to obtain this, the and Caracas and Tariq's method, and we have some other methods to look at the pressure losses that happen in the perforations. Okay, McLeod suggested from his experience that permeability of the compacted zone is 10% of the formation permeability if perforated over balance. So it depends on, are you doing the perforation over balance or are you doing the under balance? This depends. So 40% of the formation permeability. So in both cases, the permeability is reduced in both cases. So it is 10%. In this case, is 40%. And that's why the perforation is a very sensitive job, and we have to be careful for the perforation. So what are the equations that are used in the perforations? So the pressure losses from the sand phase, remember what is the sand phase? I'll make a small, okay, this pressure, sorry, I lost it. For example, this is the well. This PWF sand phase is talking about outside. This one is talking about the inside. So this pressure is outside, this pressure is inside. So what the difference between them is the pressure loss. What is, for example, pressure here is 2000. Pressure here is, let's say, 1600. So this 400 pressure drop, 2000 minus 1600 is equal 400. This 400 is dropped in these perforations that you have drawn here. That you have this we have to calculate these perforations. The pressure is dropped. Okay, and to calculate the pressure drop here, and we have an equation as AQO square plus B. So we have the A and B, and we look at do the sensitivity study that So we have to calculate the pressure drop, and okay, we calculate the pressure loss through perforation for 2, 4, 8, 12, 20, and 24 shot per feet, and the flow rate between 100 to 1200 standard. And then you develop the relationship between the Q versus delta P. So you have the data given: permeability, reservoir pressure, external radius, thickness pay zone. This is the pay zone thickness. This is the total thickness. This is the production well radius. This is the LP. This is the permeability. So we have all the data. The fluid data is density, formation volume factor, viscosity, all data is given. We put it in the equation. We calculate first A and B here. We calculate A, we calculate B. Once we have A and B, okay, we calculate the BO. After we have the A and B, we this is the equation that we are going to use. Where now well flow rate is kept. Okay, so in this case, let me share with you. Now we have this equation to calculate the flow rate. So well flow rate we kept this one, barrels per day. Okay. Shot per feet are given here. For example, 2, 4, and the perforated interval, which in this case was 20, is given previously. So you put this information here in Q. Okay. You calculate these two. Uh, this 0.16. This is calculated before from this. If you look at the okay, here it is. You calculate the A and B. Okay, and A and B are calculated here. It's 26. This is the 26 here, calculated using this equation. So you have already calculated A and B. You calculate the flow rate. You put it in the delta P. You get the pressure drop. So now, for example, if you explain this chart here, this one or this one, when you have 2 shots per feet, the flow rate will be 2.5 barrels per day per perforation, and the pressure drop will be 67. But if you have 4 shots, okay, the flow rate will be 1.25, and but the pressure drop will be reduced from 67 to 33. So it means that from 67 to 5.5. So if you increase the shot density of the perforation from 2 to 24, the pressure drop will be less. And how much exactly using, you can calculate using this one. This is 100 barrels per feet. Okay, this is the 200 barrel, 400. So in this case, so as you see that as you are increasing the shot per feet from 2 to 24, the pressure drop is decreasing from 67 to 5.5. As you know that our job is to reduce the pressure drop, and it means that we have to put lots of perforations, more perforation, but how much you can put. So this tells us that how much, and at the same time per perforation will be 0.208 barrels per day. So that's how we calculate this one. So what you need to do, you will be given this all data. You will first calculate the A and B using this equation A and B. All data is given here. Once you have A and B, you calculate the flow rate based on the shot per feet and barrels per day of shot per feet and the well flow rate, which is the 100. So in this case, this flow rate is this one, this shot per feet is this one. When you have these two, perforated interval is given, which is 20 feet. uh, so then you calculate the flow rate and you go on. You calculate this one. So now we will talk about the gradient curve, and we continue in the next video for this one. See you in the next video.